Okay, so if we're trying to draw the Lewis structure for these first two different substances, first we've got to know what we're working with. It gives us the name, and we have to turn that into a formula, just like what we were doing in Unit 4. And as soon as you see this prefix tetra, that means 4. And that means that all of these covalent compounds are going to have prefixes in their names, like boron trifluoride. Tri means 3. So that's telling you how many of that element you've got. If your element doesn't have a prefix on it, then that just means you've got one of it. So carbon tetrafluoride, carbon is C, fluoride means fluorine, which is F. Tetrafluoride means I have 4 F's. Boron is B. Trifluoride means here I have 3 F's. So this is what structures we're going to be drawing. And before we go too far, we actually have to add up the number of valence electrons that each of these elements brings, because the valence electrons are the ones that participate in bonds and kind of form our molecules. So we have to look at the periodic table and count up how many each of these atoms brings with it. So if I pull up my periodic table here, our boron brings 3, carbon brings 4, and fluorine brings 7. So I'm just going to work through each of these kind of separately, but that's where I'm getting these numbers from, is from the columns, the number of valence electrons that they have on the periodic table. First column has 1, 2, 3, 4, so on and so forth. You can find those by looking at the A numbers that are above each of the columns. A nice little shortcut for you. So back over to our packet. So here, now that we know this is CF4, that means we have 1 carbon and 4 fluorines, and that carbon brings 4, and each of those fluorines brings 7. And what's important is that we have 4 fluorines, so we have to add up 4 7s in our total, and that means that we have 32, not just 2, 32 electrons to work with. Now, these are going to be in our bonds, the lines that we draw, and in our lone pairs. All of those are going to count as electrons when we are drawing this out. So that's the maximum that we have. Once we hit 32, we've got to stop. So here, the next step, after we know how many electrons we have to work with, we're going to arrange our elements, and that means we have to choose which element is going to be in the center, and it's generally going to be whatever we have one of, or according to our podcast, the least electronegative element, so the farthest away from fluorine, because fluorine is the most electronegative element on the periodic table, which is handy for us. That means it's definitely going to be the carbon, and down here it's going to be the boron in the center. And then we're going to be putting those 4 fluorines around the carbon, and if this is a molecule, which it is, then they have to be connected to each other. So as we're drawing those F's, we're also going to draw single bonds. And I don't know why it bothers me that this one's so far away compared to the others. So, count your electrons, arrange your atoms, and now we've used 8 of our 32 electrons, because each of these lines represents 2 electrons. So we've still got a lot more electrons to place, and we're going to add the rest of those electrons as lone pairs if we can. If we run out, we might have to start making some double or triple bonds, but we only make double or triple bonds if we run out of these electrons before all of our elements get full and happy. And every element other than hydrogen, who wants 2, and boron, who wants 6, and we'll talk about that when we get to it, every other element wants 8 electrons around it. So if we look at carbon here, if we kind of look at this square box area around carbon, it has 8 electrons around it because there's 2 in each of those bonds. So even though it's sharing those 2 electrons with another atom, carbon is surrounded by 8 electrons, which is what it wants. Each of these fluorines, on the other hand, that wasn't my highlighter. Each of our fluorines, on the other hand, only have one of their sides filled up. So they only have 2 electrons. And what we're trying to do is get them to have 8. So we're going to place those lone pairs on these other open sides, kind of around those 4 sides. Because once 4 sides each have 2 electrons on them, then that is going to mean that it's full. So this fluorine is full now. And in total, I've used 14 electrons. We had the 2, 4, 6, 8 from the bonds, and then 10, 12, 14 when we added 6 more non-bonding electrons. So let's make the other fluorines look just like that. So this is 16 total electrons used, 18, 20, 22, 24, 26, 28, 30, 32 exactly. I have used up all of my electrons, and if I look, every single one of those fluorines now has all 4 of its sides full. And so they all each do have 6 non-bonding electrons. 2 bonding electrons gives them each that total of 8 that they want. So all of my atoms are happy, and I've used exactly how many I started with. So this is my finished structure, CF4. Now, I'm going to go ahead and analyze this structure while we have it here so that I can draw out BF3 here in a second. So the next things for us to do are our electron and molecular geometry. And those two come down not to what the elements are, but to how many of them. The number of kind of things, bonds and lone pairs, the electron groups are around our central atom. So in our electron geometry, what you need to remember is that our bonds and our lone pairs are both visible. We're seeing all of the electrons in our electron geometry. So we're kind of adding up the total things around our atom. And then our molecular geometry is where we only pay attention to the shape made from the bonds. Now, in carbon tetrafluoride, that's actually going to be the same, because as we're looking at our central atom, our carbon, we only have 4 bonds around it. So I'll write that here. 4 bonds. There's no lone pairs on the central atom, and that's the only ones that matter to us. So in our electron geometry, where we see bonds and lone pairs, 4 plus 0, we're seeing 4 things. Well, this is going to be tetrahedral. It's as if all 4 of those bonded atoms are balloons. And even though this might look kind of like a nice flower, a nice flat shape here with those 4 balloon shapes around the central atom, like you probably saw when I had the real balloons in class, when I hold those up, they don't want to stay flat. They make it that tetrahedral shape. And if you got balloons at home, you can do the same thing. Just blow up 4 balloons, tie them together, and they're going to make this tetrahedral shape. They don't want to lie flat in a nice square. And in our molecular geometry, where we only see bonds, I'm trying to get rid of that circle around the center because I don't like that. There we go. Well, even though all we're seeing is the bonds, we still have 4 bonds. So we're seeing a shape made from 4 things. So that means that we're going to be seeing a tetrahedral geometry again. So one of the things that I mentioned when we were learning about this is that when we have no lone pairs on our central atom, because those are the only difference between my 2 different geometries, if there's no lone pairs, then there's no difference. You're going to end up seeing the same thing, seeing the same shapes, and these 2 names will match. Now, our molecular polarity, we're looking for whether or not we have bonds, or not bonds, wow. If we have lone pairs on the central atom, and I'm going to use a different color other than red. I'm trying to color code this stuff if you hadn't noticed. So green stuff is all polarity. Maybe I'll underline polarity that way. Okay, so if we are polar, if we have lone pairs on the central atom, which we do not here, as we already saw, we only have 4 bonds on that central atom. Or if our outer atoms are different. So in this case, that is also not true. We have CF4. But if one of these was an H or anything else, even if it was a Cl, if I had 3 Fs and one of them was a Cl, even though the rest of this molecule would look exactly the same, the electronegativity of that different element around the outside means that this is going to be a little bit less electronegative than the other side. So this side is going to have a little less electron density than the other side, which is going to start to make me a slightly polar molecule. So this does not have either of those two things, though, as written. CF4 would then be non-polar. As a non-polar molecule, every molecule that's non-polar automatically only has London dispersion as its intermolecular force. Because you have to be polar to have dipole, and then you have to be superpolar to have hydrogen bonding. So if you're not polar, you don't have any other option. You got to be London dispersion. And this does not have resonance, because resonance is going to involve having a double bond. If I had a double bond here and everything else was single bonds, then that would make it look like I could have put that double bond anywhere in that molecule. So that's what we're looking for resonance. And since we don't have any double or triple bonds here, we can't have any resonance. So that is it for this example. And now I'm going to erase this structure just so that we can have a little bit more space, really kind of those answers here. We can be focused more on this stuff and how it applies to BF3. So, boron trifluoride. If we start with drawing the structure, we have to add up our valence electrons first. 3 come from boron, 7 come from each of those fluorines. Remember, we checked the periodic table earlier and looked at the column numbers to find these numbers. So this means that we have 24 electrons to work with here. We're going to start by arranging our elements. B in the middle, the F's bonded around the outside. I'm going to scooch that line up just a little bit. Try and fit this in the space we've got. And now I've used 2, 4, 6 electrons total, and I've got 24, so I've still got plenty, and I'm going to do the same kind of thing with these F's. Starting with our outer atoms, trying to fill up all of their outside edges. F is good. Now this F, that's 18 electrons so far if you weren't counting. 20, 22, and 24. So we've used up all our electrons, and normally, if this was anything other than boron, we'd have an issue here. Because our boron looks like it's got an empty space here up on top, where I really wish I had 26 electrons. If I had 26 electrons and this was anything other than boron, then this would be a nice happy molecule. I just put those dots there. But I don't have those dots to give boron, and it's actually a good thing that I don't, because boron doesn't want them. Boron is one of the only elements other than hydrogen that only wants 2. Boron only wants 6 electrons around it, and then it's happy and fine and full. So this is our BF3 molecule. And I want to analyze this real quick, just to be kind of finished with it, and then I'm actually going to come back to this and do a couple variations of this to kind of show you some other examples, because both of these first two examples are pretty plain. They follow all of the rules except for this one octet rule thing. So I want to show you a couple more examples, so I'll come back and change this up a little bit, but this is the correctly drawn structure right now. And so if we are beginning to analyze our electron and molecular geometry, remember, in our electron geometry, we see our bonds and our lone pairs. So I have, and we're just paying attention to our central atom, I've got 3 bonds here, no lone pairs. So this is going to be slightly different than our first example because we only have 3 bonds, and the shape made from our 3 groups around our central atom can kind of be depicted by 3 balloons tied together. And our fancy chemistry name for that shape is trigonal planar, because they make a triangle, but this is a flat triangle. One of the examples I'll talk about a little bit later is if we did have a lone pair on here, then our molecular geometry, even though all we would be seeing, technically, I'm not going to get into that. We'll get into that when we see that example later. So here in my molecular geometry, where all I see are bonds, I'm still seeing 3 bonds. So that's going to be trigonal planar. So names are the same when I have no lone pairs. Again, like I said, kind of boring. Polarity, I see no lone pairs on my central atom, and I do not see any different outer atoms. So once again, this is nonpolar, which means automatically this only has London dispersion forces, because everything that is nonpolar has London dispersion. And also, once again, because we have no double bonds, it means that we are not going to have any resonance, because we can't have resonance without double or triple bonds. So this is our second example. Now, like promised, I'm going to do, I actually might take this off of this page so that it looks less confusing, because I don't want you to think that I'm changing BF3's structure because it was wrong or anything. So let me clear this out real quick. Okay, so these are now kind of imaginary versions of that BH3 molecule, or BF3 molecule, just so that we can pretend here that our X isn't B. So let's pretend either we forgot that boron was an exception and we thought that it needed 8 electrons, but we still just had 24 to work with, and we've already placed them all here. If we either forgot that it didn't need 8, or if we were just confused and didn't know how to deal with it, then when we run out of electrons, what we do is that that X in this case, wants electrons there, but we don't have them. What we do is take lone pairs from one of the atoms that is full and happy, in this case our Y, and move them into a double bond. So that Y now has less dots around it, but it still has the same number of electrons, 2, 4, 6, 8. It's just sharing more with X now, instead of having its own dots here all to itself. And that helps X out, because now it has its 2, 4, 6, 8 electrons around it, and yet we still only have 24 electrons in this molecule. So we've still obeyed the rule. So if you did accidentally forget boron was an exception, or you didn't know to begin with, this is probably the molecule you would end up with. Now, the good news about this mistake, as long as you count your electrons correctly, looking at this molecule with its electron and molecular geometry, we're still only seeing 3 bonds and no lone pairs, because this right here is a double bond. And listen to that pronoun. That's a double bond. So that's 1 bond there. It's just twice the strength. So because we're seeing the same things, this would actually be the same trigonal planar answer that we had gotten before. So if you forget about boron's exception and you end up with that double bond there, you're going to get your electron and your molecular geometries right still. And technically, you would still even get your polarity right, because we still don't see lone pairs in our central atom, and we still don't have any different elements around the outside. Doesn't matter about the bonds there, one being double versus single. This would still be nonpolar, so you would still find this as London dispersion. And the only place where you would mess up in this is with resonance, because now we get that resonance idea. We have a double bond here, and why did I decide to take this electrons from this Y? Couldn't I have done that to this other Y instead and move these electrons over? I sure could. And in real life, that does happen, that it'll just switch sometimes to having a double bond on another place. That's what the idea of resonance is, that the molecule has options, and you have options when you're drawing it. So that's the only mistake that you would make if you count your electrons right. You just place them wrong and forget about that exception. Now, in this last example here, this is also another way you might make a mistake with something like BH3, either in when you're analyzing it or drawing it or both. If you don't count your electrons correctly, and a lot of people don't for whatever reason, I don't know if it's just hard or they forget, or they just like, oh yeah, BH3, or XY3, I'm gonna just put X and Y and then just fill up all the rest of the spaces with electrons, which it would get you something like what we see over here. And if you do that, when we're analyzing that structure, which supposedly would be BH3, because here you actually have used 26 electrons, this entire structure is now going to be wrong. All of the rest of this analysis that we're doing over here is going to be completely wrong. I guess except for resonance here. Ironic. Just because you didn't take the time to count your electrons, or maybe as you were placing them out, you didn't count correctly, or you skipped over a number and you didn't double check. So it's easy to do. But this is where you're going to mess up, and this is where you get some more interesting geometries here. With lone pairs on our central atom, I'm going to color code these. I have 3 bonded groups around my central atom, and then I have 2 non-bonding electrons, 1 lone pair on my central atom. And in my electron geometry, all of those groups look the same. We're considering them the same. I'm seeing 4 total groups around my central atom. That is going to be a tetrahedral shape. I'm actually going to get rid of these kind of blobs here. So all of a sudden, I add that lone pair to my central atom, and my electron geometry is now tetrahedral because it has 4 groups around it. Now, you might think, okay, well, when we get to our molecular geometry and we're just looking at our bonded atoms, then at least it would be the same. But it's not, because even though we're only seeing these 3 bonded atoms, we are still having an effect from those lone pairs. So kind of filling these in with that green highlighter. We don't see them. They aren't concrete. They don't add to the shape of the molecule, but they can push on the electrons that are involved in those bonds on our molecule. So instead of being trigonal planar, if I have 3 bonded groups to the central atom and 1 lone pair, that's going to push those 3 groups into kind of a pyramid shape. So this is when we end up with our trigonal pyramidal geometry. So completely different shapes, all because of that lone pair there. And because I've got a lone pair on my central atom, now this molecule would be polar. And because I'm polar, I would have at least dipole-dipole as our IMF, and if that was hydrogen, as our Y's, and any F, O, or N in the middle there as our X, then that would also have hydrogen bonding. This doesn't have resonance because we don't have any resonance, because we don't have any double bonds or triple bonds, so those couldn't be moving around and have options on where to go. So you would still get one answer right, but you'd get 1 out of like 6 things, all because you didn't count your electrons right. So don't forget about that step. It is an important one, and that can determine a whole lot of other stuff about your molecule. Now, I know I did a whole lot more than what you were asking for, but hopefully those first 2 problems help actually do stuff in those packets, and then maybe these other ones maybe help you with some of the other stuff that can happen with some of these structures. So either way, I hope it helps. Let me know if there's anything else I can do, although probably not any more 25-minute videos. We'll see.